Welcome back to System Software. So I hope you all had a good break. Before we left for the break, we started on lecture 10, where we were talking about how variables and expressions, how we generated code for those, and what the assembly language, or at least one version of the assembly language equivalent program would look like for our simple C programs. But we didn't finish it, so I extended the Project 3 by a week. I know it doesn't give you like more time in the semester or anything, but these two projects are similar. So when I go over today the approach that for generating code for the code generator, hopefully that should carry over, or that will carry over to the next project as well. Okay, so last time we reviewed functions and how functions are generated, and we went over some of the assembly language instructions, I think, right? Some of the assembly language instructions, and how I've given you some macros to help you generate those instructions, so you don't have to, write printf for yourself. And plus, it also gives you a small finite set of instructions that you can use for the entire code generation project. And I think where we left off was actually going into more detail about how to do this generation. Okay, so let's start with an example program that I hope will help motivate what this looks like. Let's take this simple C program here. I've got one function definition, f. It takes a single parameter a that has type int. It declares a new variable y. It assigns that variable to 2. Then it computes a, the input parameter, plus y, and returns that value to whatever the caller is. Inside of main, I declare a new variable x, assign it to an expression that computes 7 times whatever the result of f of 3 is, and then there's just a series of example expressions that I assign x to. And at the end, finally, we return whatever the value of x is at that point. Okay, questions on this example program? Okay, let's go over some of the assembly language instructions that we can use to make it equivalent to kind of emulate what we think this program is supposed to be doing. So first of all, this is kind of a review of several weeks ago. This assignment statement. So when I assign something to y in a function, in this function local variable, how does this get stored in the machine? At least using the conventions that we talked about several weeks ago. Yeah.
Stored in the stack, right?
That's right. Yeah, exactly. So we store it in the stack. So if you recall from, I know this was several weeks ago at this point. But if you recall our long discussions on stack frames and how function calls are done, at least in the Intel x86, 64, 65 ABI, function local variables get stored on the stack. And so each stack, or each function has its own stack frame to hold all of its function local variables. And if anyone can recall, what was the purpose of using a stack for this? Why not just use the heap or pre-allocate some memory? Why bother using a stack for this? For function local variables. Yeah. What's that? Speed? Well, not necessarily. You could hold the variables in registers, and that would be faster. So if you're really concerned about speed, you may avoid using memory altogether. Yeah?
Does it
Well, that pushing and popping is how we created the stack. Well, remember the fact, oh yeah, okay, go ahead, yeah.
So we got a new copy for function call?
Yeah, so the idea was to have each function call have its own copy of the data. And so we made a new stack frame for each function call. And this is because of that factorial example. If you remember with factorial and these recursive function calls, if we don't save the data for each instance of the function, then we're going to overwrite that data for multiple recursive calls. So I guess just as a quick refresher, when we had our factorial function, if we say made a new variable like so, and we return so this is one valid version of the factorial function. The problem was that if we don't save a copy of y for each instance of factorial that we call, then it's going to be overwritten by the subsequent calls. So for instance, if we're calling f of 3, then this will eventually call f of 2, which will call f of 1, and so on. And each versions of these will use this variable y. So if it always uses the same register or the same memory address, then when we call new versions of f, when we call f again recursively, those new versions are going to blow away the value of y. And when we come back to the function, and if we need that value, it's going to be the callee's version of y. Does everyone recall this? This is hopefully refreshing memories a little bit. The idea is that the abstraction of a function is that each function call has its own local data, each call. It's almost like we're dynamically creating a new version of that function at runtime. You could think of this as creating a function called f3, which takes no values. It's as if we're creating 3 new versions of the factorial function, one for each argument value that we pass in. And the way we implemented that was using a stack. And so on our stack, each copy of f, like this is f3, this is f2, each copy had its own copy of the local variables. So f of 1, never assigned y, but each instance of our call to f had its own local variables. What else was stored on this stack to help implement this function abstraction? Does anyone recall what else we needed on this stack in order to restore flow control? Yeah. Right, that's right, the return address. So another thing we needed to store was the return address. And what was this for? What was the point of having the return address? Or why do we need it? Yeah.
So we can restore the prior stack frame.
So the return address is the next line of code in the function to execute. But I think you're thinking of something else, another part of the stack frame that's stored. And what's that part? That's the base pointer, exactly. So the base pointer, at least in the Intel world, is a register that always holds a pointer to this stack frame. That's RBP. And so we also save that the pointer to the stack frame of the caller, the function that made the call, because the idea is when we go to make this function call, if there's any computation after the function call, we have to return to the caller function. So we call fact here again, but this instance, f3, well, it hasn't finished executing yet. So what the stack allows us to do is it allows us to freeze all of the state of that function and to go off and run a new instance of the function. So in order to continue executing that frozen function, we need to know what the next instruction in that function is to execute to start continuing execution. And we also need to know where its function local data, its stack frame, is stored. And so that's what these two pieces of the stack frame hold. This information, the return address and the saved RBP, this is information about the previous call, the caller. It's stored in the callee's stack frame, but it's information, enough information to allow us to restore execution in the function caller. Questions on that? Quick review of the function stack. And so I went through the debugger and walked through it, so you can check out lecture 9, I think it was, if you'd like to review the steps of that, or just run the debugger yourself as well. Okay, so by convention we're going to use the stack in order to store Y. So what kind of instruction can we use to store a value on the stack? So the stack is just in memory. So I know you may not know Intel assembly, but I think you know some assembly. So what assembly instruction might you use in order to store some value into the stack? Yeah. Push is one. Yeah, push is one way to do it. Other instructions for, yeah. What is it? MOV? Move? Yeah. So it's like an abbreviated form of move, yeah.
Do you need to use sub to allocate spaces?
Oh, okay, good question. So we can think of the declaration as an instruction to the compiler to say, give us space, allocate space on the stack for us. So one way you could do that is to use push. Push actually will do both allocating space and writing to memory. But we also have the suggestion of using subtract. Subtract from what? So we have, since we're storing on the stack, which register address tells us where on the stack, where in memory the stack is located, if anyone can remember. It was also on this page, I think. Which register, at least in the Intel world, stores the position of the stack in memory? Yeah. RSP, exactly. So RSP is a register that by convention is supposed to hold the top of the stack, and RBP holds the pointer to the stack frame. Okay, so we have a lot of options here. We can use subtract to modify this RSP pointer. We can subtract from it. So we actually need some value here to subtract from it. And we can use move to store this value of 2 into whatever the address we have of Y. Now, alternatively, you absolutely could use push as well. You could do this whole thing by just pushing the value 2 onto the stack. So that's a little too clever for me. In my implementation, I do subtract to set up the parameters, or set up the local state, and I use move separately. And the reason I do this less clever way is because it's easier to implement the code generator. So the strategy I'm going to give you will allow you to not have to think about multiple instructions. You can just translate one instruction at a time, and we're just going to make sure that they work together using some conventions. But you absolutely could optimize this by just using push instead. You can even optimize it further by seeing if you can avoid memory altogether and just using registers. For that kind of more sophisticated compiler generation, there's a graduate compilers course that I teach, so if you're really, really interested, you can take that even as an undergraduate. But I'm going to show you the simplest method that at least I can think of for generating code for this. And effectively, you can think of it as line by line, statement by statement, expression by expression, what snippet of assembly can we generate without thinking about any other instructions that will create an equivalent version of this program. Okay, good. So what about this A plus Y? So how could we, what code might we generate, assembly code might we generate to execute this instruction? Yeah.
When you move the A into the stack from the register?
Oh, so this is a good point. So I thought somebody might say, we'll just use the add instruction, which you definitely need to do. But then the question is, well, yeah, where do you get the data from? Where do you get the data from for this add instruction? So if you look at the Intel documentation, I don't think it's possible to add 2 memory locations. You need at least 1 register to do your add. So before you can even do this add, you need to get some data into registers. And as a simplification, to make things easy, because when I show you an example of doing this through the tree, my goal is to have every operand in a register before I do the instruction. And I'll show you on the tree why that makes it convenient to do this. But yeah, we need some way to get this data into a register. And so what instruction do we use for that in the Intel world? Yeah. You could use pop if it's, yeah, exactly. So you can use pop to get whatever the value is off the stack. So now the challenge here is that depending on the order of these instructions, if we pushed Y, there may be some other interleaving instructions that mean it's no longer at the top of the stack. So, yeah.
So can you pop all the parameters, like, before you do, like, the code inside the function, like, while you manage the function, off the parameters, off the stack?
So that's one way to do it. So if you knew you could allocate all registers for the function, you could absolutely just keep them in registers the whole time. I'm going to show an even sort of more kind of brain dead, very, very simple way to do this. And actually, might as well just go into the tree to show you, kind of motivate why I made the decisions I did for this. Because one thing I'm bumping up against you here is that there are a million ways to translate this program into assembly. And so let me show you one, and this is not the only one, but one way that I think will make implementing this code generator a little bit easier. And the idea is just like the type checker. We walk over the tree, and then for each node on that tree, we generate one simple assembly language template. And the only trick we need to do is make sure that whenever we generate code for each individual node, that all of the code together will be an equivalent program. And the key here for me is to reduce having to think about entire subtrees. I just want to think about one node at a time. And so all of these clever optimizations that you guys are coming up with, well, okay, let me keep things in registers, let me push instead of using two instructions. I'm going to just throw out all those clever ideas and do the most sort of brain dead, simple thing that I could think of doing. So okay, so let's take this whole tree here. So I've got this function. And, let me just do a plus y. Let's do a plus y to start with, and then we'll look at the whole function. So if I've got a plus y, I have a binary expression. And a binary expression consists of some other expression on the left. In this case, it's an ident expression. And this ident expression has a. It has an operator, and it has another ident expression, y. So I'm going to make the assumption that I've already prepared my memory when I enter this function so that all of my variables in my function are on the stack. Yeah, I don't have my pointer, unfortunately. Okay, so for variables, whenever I see an ident expression by itself, the convention I'm going to use is that whenever I'm finished an expression, the top value on the stack is going to be the value of that expression. So by using that convention and making sure I use it in every single expression, I can be sure that whenever I get to the parent, I don't have to think about what operation was done here or how it got data. I can just look at the stack, the top of the stack, and say, oh, okay, that's going to be the value of the thing I just did in the child. So that's the main convention that we're going to use, or at least that I suggest you use. And you could certainly implement this however you like, which will make equivalent code rolling in a test, the I/O equivalence. But the convention that I'll recommend is that whenever you evaluate an expression, just push the resulting value onto the stack. Okay, so that means for A here, so actually I can just make this full screen now. Okay, so in red, I'll put the assembly instructions in red. So that means as the last step for all of this, I'm going to do a push to push the expression onto the stack. Another convention I'm going to use is to always use RAX as my destination for everything. Now, this is terrible register allocation. There are lots of registers you could use to make this better. But to make this easy on myself, I'm just going to use RAX as the resulting value for everything. So this will be the last instruction of every expression in your generator. But we also need to get RAX filled with the value of A. So in order to do that, I need move. And I need to move from some memory location to RAX in order to get its value and push it onto the stack. With me so far? Any questions about this? So this is by no means the only way to do it, but every ident expression, the kind of template, the code template will be, that at least I recommend to use, is to move whatever the address of A is into RAX and then push RAX. So similarly for this ident expression, there'll be a move from some memory location into RAX and then push RAX. And before we get into actually how to compute the memory location, let me finish up the binary expression, so you can see how using this convention makes it kind of simple to figure out where the parameters are and actually do the operation. So what's the last thing we would do on binary expression, in my convention at least? Yeah?
Pop those off the stack and add them.
Add them, right. Well, what's the last thing? And then once I add them, where do I put the value, at least in the convention I'm giving you? Push it again, yeah. So working backwards for binary expression. By my convention, I'm just going to keep everything in RAX and push that as the last thing for my expression. And then, your classmate already gave you the things we need to do, so we're going to pop both these values off the stack and then add them. So in my convention, I want to be able to have the resulting value be in RAX, just by my convention. I mean, you can use any convention you like, but I recommend this one because it's easy. Okay, so we have two values in register that we need. We have our destination register RAX. We have our push instruction for our convention. So we need another register here. So by convention, I'm just going to use RBX for all other, if I need two parameters for an instruction. So this is just a recommended register allocation scheme. You can feel free to be as clever as you like. I recommend doing something very simple that's easy to remember. And so I make these very specific constraints, like always push the value into the stack, always use RAX as the destination, and then it just makes it easier to write the code generator. Okay, so why is it that we can just call pop in order to get these values off the stack? So if we're in the binary expression code generator, and we've called the code generation for ident expression on the left and ident expression on the right, why is it that we can just use pop in order to get those values? Yeah? Exactly. Yeah, that's right. Exactly. So, and this is just a convention, but this is what makes my convention a little easier to use when running this code generator. So we can just call the code generator for ident expression in isolation without thinking at all about whether it's an addition operation or where it's going to be used or how it's going to be used. We don't have to care about any of that. Instead, if we use the convention that every expression always pushes its value onto the stack, then once we get to binary expression, it doesn't matter what the left and right operands are. It could be another binary expression. It could be constant. By having this guarantee, when we go to generate binary expression, as long as we've called the code generator for the left and right operands, we can be guaranteed that they're pushed onto the stack. Okay, so if we call pop twice, which operand is going to be pop first? Or do we know? Or how do you know? Yeah.
If you push A and then Y, then you would be popping Y and A.
Very good, yeah. So, it's first in, last out, right? So it depends on the order that we push these two things. So again, by convention, I'm going to just call the code generator on the left operand and then the right operand. And if I do that, then the left operand is going to be pushed first. So if I show the stack here, if I call this one first, then my stack is going to have the, growing downwards, it's going to have the left operand and then the right operand, and my stack pointer is going to be pointing at the right operand. So when I go to call pop, which operand am I popping off, the left or the right? So the right one, yeah. I pushed left first, then right. So the right operand is going to be popped off first. With my convention, I'm going to put the right operand in RAX and the left operand in RAX. Okay, so now we've got the data from both the left and right operand. We've added them together and pushed them onto the stack. So why is it that the add instruction in this AT&T syntax, why is RAX on the right, even though it's the left operand in our instruction? Or did I make a mistake here? Yeah.
Because when you push the stack and pop it, it forces it. So you have to put it in your addition.
Well, we popped the right one off first. So RBX is indeed the right operand. There's a much dumber reason for this. It's just that the AT&T assembly syntax convention puts the destination operand on the right instead of the left. The Intel conventions put the left. So I just want to make remind you that because we're using AT&T syntax, the destination is on the right, and that means for add and subtract, the destination is also the left operand in the Intel instruction set. So it's just an idiosyncrasy of the Intel architecture. That's the only reason for this. No fancy reason. I just want to remind you that the destination is on the right for this. All right, questions on this so far? Questions on this? So if we generate all this code in a post-order tree traversal, we'll call binary expression, and this will recursively call ident expression, produce the code here, go back to the parent, recursively call a generator for the right expression, produce this code, and then once we're done, we'll produce the code for the parent. And if I can pull this off, what the code will look like is we'll have a call to the left instruction here, be emitted, be printed out, and then a call to the right expression will be printed out, and finally the parent call. Will get printed out. And so we should see, if you have a code generator that follows my convention, we should see this sequence of instructions. So seeing it all together, it just looks like kind of assembly gobbledygook. But if you just keep in mind or make comments to preserve the ordering of this, to preserve the chunks of code that we emitted for each node, this is what we'll see in the final program. Questions on this? Yeah.
The order subtracting instead of adding with RAX will be on the right, like the order still.
Yeah, so for all of the arithmetic operations, the left operand is the destination, and the destination register is always put as the second argument.
In that case, it wouldn't really matter because addition is commutative.
Yeah, addition doesn't matter. Yeah, that's right. Addition doesn't matter actually, yeah, because it's commutative.
Subtraction, that order would still.
The order would, yeah, this would be the order for subtraction.
Okay.
Yeah, that's right. So actually, it may not matter if you do this. I mean, if you swap these two, then RBX would be the destination, but you want to make sure you push RBX. So that's why I use this convention to make it easy for myself to do the code generator, to just say, all right, I'm always going to make the destination RAX. So then when, you double check the instruction, which one's the destination, it should always be RAX and always push the value onto the stack. If you use those two conventions for register allocation, it should be much simpler to do the code generator. And by all means, if you can think of more clever ways, more efficient ways to do this, let me know. You can use them for a bonus project, or if you have some other clever idea to reduce the number of instructions. There's decades of research on compiler optimization, reducing or improving the performance, reducing the number of instructions. But I'm going to leave that out of this class because it complicates the job of code generation. Okay, so this is the code we would expect to see for this A plus Y. So now let's take a look at the actual assembly output, at least of my generator. And without going through the whole assembly instructions yet, you can see here I have this commented to generate code for the left operand. So there's our move and push. Generate code for the right operand, there's our move and push. And then here's the pop of the two operands, there's the addition, and there's the push. So that's implementing this exact strategy. And the reason that I was able to do this is I use these conventions to make sure that I only need to think about how to generate code for one node on this tree at a time. That's like one of the key ways to reduce the complexity of doing this exercise. Follow these conventions. You should only have to generate code thinking about just that construct, just that node. Okay, questions so far on this? So keep that in mind when you're doing this. Think compositionally. Think, what's the code I need to generate just for this node? And make the assumption that your other calls are correct already. Just like with parsing and type checking, work bottom up, start with the simple ones like ident expression, and work your way up, testing along the way. Okay, so let's talk about how we actually fill in these memory addresses. And to do that, let's revisit our calling convention. So as another way to simplify things for this compiler project, my convention for the function calls is exactly the same with one small addition. Instead of, to motivate this, the difficult part about using Intel's 64-bit convention is that some of the parameters are in registers and some of them are on the stack. So to simplify things, I'm going to add all of the parameters to the function stack in our implementation. And so I think I've given you code to help you do this, so you shouldn't have to worry about this. But what this means is that our stack frame will look something like this. Oh my God. Also, as a simplifying thing for our project, you only have to pass a single parameter. But if you want to do the full project, you'll end up having, this will be parameter 5, parameter 6, parameter 7, parameter 8. And so where are the first 6 parameters stored? They're in registers. So just like this convention here, they're in this convention here, they're in registers. So I'm going to make all this easier. So first of all, you'll only have to pass a single parameter. To make this easier, you'll only have to pass a single parameter. And the way I have the stack set up so that you don't have to worry about parameter passing at all. You just immediately move everything into the stack. So we have the return address, we have the old base pointer, and then we have the parameter, and then any local variables. That'll be the convention for our stack. So for our program, we only have one parameter A and one local variable Y. So our stack will look like this. We'll have the return address, the old RBP, and A, and then Y. So following the function call convention, the current RBP will point here on the stack, and then A will be off one step away, one stack element away from the base pointer, and Y will be 2 away from the base pointer. So by following this convention, we have an easy way, or an easier way, to access all of the parameters and any local variables in our function. There'll just be some offset from RBP, some negative offset from RBP. So as a quick pop quiz, why is the offset from RBP to A, why is that negative? Yeah. What's that? The stacks go down, yeah. And this, just by convention in, I think, all modern operating systems, the stack starts from a high address and grows down. But the key for us here, to make it easier, is that if we ever want to find one of these variables on the stack, all we have to do is start with the base pointer and offset by some fixed number to point to that place on the stack. So it's just like an array offsets, array indexing. And again, as another simplification, for this project, each one of these fields in the stack will be 8 bytes for everything. So no matter what your data type is, we only have 8-byte, 64-bit data. And so as another simplification, all local variables will always be some offset of 8 from the base pointer. And so I've given you code to help set this up. So in order to manage all this, we'll use a symbol table just like we did with the type checker, except instead of storing types, we'll store offsets from the base pointer. So the reason for this is that these stack frames could be anywhere in memory, depending on the order of calling that happens in the runtime of your program. And so we can always guarantee ourselves at compile time a way to find where this variable is. Because of this calling convention, RBP will always point to the stack frame. And because of the way we insert data into the stack frame, it'll always be these variables will always be the same fixed offset from the base pointer. And so no matter what the base pointer is or where in the memory the stack frame is, we can always figure out where our local variables are by just adding an offset, the same offset to RBP. Yeah?
So due to that offset, does that mean that everything is stacked? Are they consecutive in memory? Or?
Yeah, they're all consecutive in memory, exactly. So this will be -8 from the base pointer, and Y will be what from the base pointer? What offset? 16. Yeah, I heard everyone say it. Yeah, and so on. And so I've given you all the tooling in order to set this up. So the way it'll work is when you go to actually let me get the code. So whenever you see a parameter or a local variable, you'll just insert this into a symbol table, and that symbol table will automatically compute these offsets for you and save them so that you can look them up later. Questions on it so far? And I'll show an example of this. Okay, so knowing that convention, and if this is our stack frame for this function, how can we now fill in these spaces here? So this was for A. So how do we compute the memory address of A? Yeah. Oh, very good. So you already know the syntax for it. So for those of you who are unfamiliar with the syntax, let me go over it. But that's exactly right. So it would be -8 -8. Let me do it this way. -8 RBP. Let me give myself some space. So this is what the instruction would look like. So let me go over this -8 business here. So this is just special syntax that, or actually it's a special instruction that Intel has and syntax for it in the AT&T syntax for saying, give me the address of RBP, subtract 8 from it, and then find the value at that address. So basically, because this calling convention is so common, this use of stack frames is so common, that Intel actually built in an instruction that allows you to do this kind of addressing in one instruction. So in like a RISC architecture, you might have to first get the value of RBP into a register, or it's already a register, subtract 8 from it, and then look up that value and move that value at that address into whatever register you want to move it into. The Intel instruction set has an instruction that allows you to do this just in one shot with one operation. So you don't have to worry too much about the details of the Intel instruction set. I've given you a macro that will do this for you. But here, you just remember that in the AT&T syntax, whenever there are parentheses, it says, give me the value at the address of that register instead of the value of the register. So this is in contrast to, say, add RBX to RAX. This is saying, give me the value in the RBX register. If I were to put parentheses around this instead, the parentheses would say, go to the address that's in RBX and get that value. So that little kind of esoteric syntactic change, the parentheses say, give me the memory address at that register instead of give me the value of the register. Does this look like some familiar construct in C to you? What's that? What? Dereference. It's pointers, right? It's pointers. So this is exactly where pointers, that's how they get compiled down to, and this is where it comes from. The notion of having a register value versus having the register value being a memory address and doing a load or store from that memory address. So if you can kind of wrap your head around how these assembly instructions work and the difference between getting the value of a register versus getting the address, getting the value of the address that the register has, then you'll get pointers, because that's all pointers really are. Pointers are like a mnemonic for writing this when you do star. And this offset notation, so what other constructs in C might you use this notation for? So pointers, the parentheses you'd use for pointers. But what about an offset? Yeah.
This would just be an array.
Array, exactly. Yeah. So when you have an array index, you use the brackets and put a number in there. It's effectively the same thing as doing this, where the array is some address that's stored in a register, and then the index is just this part, this offset from that value. Yeah. Depending on how many variables, you mean slow down the process of compiling or the program that gets run? Oh, sure, yeah, for sure. Yeah, I mean, these days the machines are fast enough, but sure, yeah. I mean, decades ago, compilation itself was a very expensive process relative to compute time. So sure, if you have a program with a large AST with lots of variables, big tables, absolutely, yeah. I mean, you have the same kind of classic data structure, like algorithms, worst case performance. Even if it's linear time, yeah, you still have a giant table. So for sure, yeah. And so, I mean, more like in the 70s, like this was a constraint on a compiler. But this kind of stuff is a lot, it's not really constraining compilers anymore. The big constraint for compilers now is optimization and like safety checks, like memory safety checks. But for your guys' machines, you'll have no problem. If you have like 100,000 variables in your program, you're probably still not going to see much impact on just this part of the compilation. But absolutely, it can, yeah. So good, yeah. So if you can wrap your head around this instruction, then you'll get pointers and arrays in C and why they work the way they do. They're effectively a light wrapper on top of instructions, on top of machine instructions. So if you think of the register as being a variable, then the variable just holds some number. And it's really what operation you do on it that distinguishes an integer from an address. So if we just use the register's value itself, well, that's an integer. If we use the register, this memory indirect addressing, where we use the address in a register to look up a load in memory, well, that's a pointer. All right, questions on this so far? What about the address of y? How do we find the address of y? Or how do we find how do we finish this instruction in order to get the value of y? Yeah. Yeah. So we go to our symbol table and we look up what the offset of y is. We find that it's 16. And then this instruction, give myself some space. And this instruction, just like for AX, we'll use this memory indirect load here. But it'll be 16 from the base pointer, and we'll load that into our AX. All right, questions on this? Yeah?
When you're moving the variables from the stack into the register, does it move the actual variables from the stack?
No, it's just moving it. It's just another load or store from memory. So this stack doesn't change at all. It's just a load. Because, yeah, we're not pushing or popping. We're just reading from memory, just like in a heap. So yeah, it's just a read, it's just a load. So yeah, if you're thinking about the MIPS world, I guess it's load and store, right, in the MIPS world. So load and store are all called move in the Intel world. It just depends on what the destination is. If the destination is a register, then it's a load. If the destination is an address, then it's a store. Yeah?
So is the move operation kind of like a copy operation over to the?
Yeah, it is, yeah. Yeah, so what's it called in the MIPS world? Is it copy or load or store?
I think it's either load or it's not copy.
It's load, yeah. But it's copying. It's taking the memory value and copying it into the register. And in a kind of RISC world, it would be load and store. Or in MIPS, it would be load and store. It's move for everything in the Intel world, and then there's 50 different move instructions. It's just the mnemonic is always just move. Yeah.
So move is used for loading as well?
Yep.
Storage?
Yeah, exactly. Move is used for loading and storing. So this one is load. So this is load. So remember, AT&T syntax, the destination is the right operand, the second operand. So this is loading from this memory address into this register. Yeah.
After we do that, I would just pushing it back onto the stack.
Yeah. It seems silly, right? It seems silly. Like, why bother? Like it's already there on the stack. So the difference is that this is a different point on the stack. This is at the top of the stack, at the RSP. And so, okay, so why? Or I argue that this makes it easier. Why? So let's say you didn't do that. Let's say you're just like, well, it's already on the stack, so why bother pushing it? How would this change the compilation of the whole binary expression to do that? Or what would you have to change, if anything? So let's say we didn't push it on the stack, or we didn't move. We're just like, all right, we know the memory address. So we know the memory address. We know the memory address for ident expression. What about when we go to generate the add instruction? In my scheme, we just pop the two values off the stack, add them together, and then push that value. We wouldn't be able to pop them anymore, right? Because they're not there on the stack. So what would we have to do to change binary expression if we don't push it onto the stack? Or what's one way? Yeah. Yeah, you could have a convention where you make sure that this is always stored in some register. We're going to need to tell binary expression which register each child is in, right? So to get rid of all that complexity, I just said, all right, so basically in my scheme, you don't have to return anything to the parent. There's no communication between the child and the parent nodes. That's why I did it this way. But you could absolutely use a way that is less sort of ridiculous, results in less ridiculous code. But what I want to point out to you is get things correct before fast. So if you're making sort of a micro performance optimization, you're saying, well, this is kind of silly. Why am I, and notice here that we're pushing and then immediately popping. Or actually, no, not in this case, but there'll be cases where you'll push and then immediately pop to the same register, which looks just terrible. But my message to you in this course is get things correct before perform it. And also, once you have things correct, you don't necessarily need to change your algorithm. You can add later phases that improve performance while keeping the correct program very easy to reason about. So that's why I do it this way, is it's much easier for me to reason about just thinking about what do I have to do for binary expression with the least amount of information than trying to have some clever optimization that I could always just do later anyway. So by all means, think about optimization and if you come up with more clever approaches, but this is the simplest way that I could think of to do it. Because I want to make this correct first and then perform it later. And that is actually what modern compilers do. They have a kind of very naive, simple code generator, and then there are long series of optimization steps that take away all of these kind of silly-looking things that you might not do if you were writing this code by hand. But the key is to just have that correct, easy-to-verify step, and then use later phases to make it faster. All right, questions on this? Okay, so let me show how this table gets constructed. We have this function here. So we have our function here. This is what the AST looks like. It's got a name F. It has a list of parameters A. It has a type. And this is all just from the AST specification. It has a declaration list, a statement list, and then a return expression. So the way this will work is just like all of the stuff in the front end of the compiler, we traverse this tree in a post-order fashion. So when we see F, in the type checker, we would put this into the global symbol table. There's nothing we need to do for code generation because we can actually use F as a label in assembly. When we get to A, here's our first local parameter. So the way we're going to keep track of these offsets is to have a table, a symbol table, that stores the name of a symbol and its offset from RBP. So this is going to be the offset from RBP. And so I've given you functionality to just call insert, and whenever you call insert on a symbol, so here if we call insert on A, it'll automatically compute the offset for you. So the only thing you need to do is just make sure that you're traversing all of the places where you have local variables. And for functions, there's only two places, either the parameters or the declarations. So inside the declarations here, there is this int y inside of the declaration list. So we traverse this tree. We see A. The type isn't useful for the code generator because we've already done type checking. And then when we go into declaration lists, for each one of these declarations, we insert that symbol into the symbol table. And the tools I've given you will just automatically, whenever you call insert, it will just keep track of the offsets for you and add the symbols. So if there are other symbols in here, you would just keep getting new offsets to the symbol table. Questions on this so far? So that's how the symbol table gets constructed. So just like in the type checker, we construct a symbol table. And then when you need to go actually when you see an ident expression and you need to actually get what the address is in order to load it into a register, you just use this same pattern. You use the memory indirect offset addressing from RBP, and then in order to get this value before the parentheses, you just literally look it up in the symbol table and just literally copy it right there. Questions on this? So let me show some of the code for this. Well, first, actually, let me show you the variations of move that I've given you. So move immediate, this is for constants. So immediate values, that's just when you literally put the number in the instruction and this gets copied to the register. And this is move from offset. So it's probably a little tricky to parse this printf stuff because it's done for spacing. But you can see here that it's a negative digit, negative integer, parentheses, and then RBP. So this is part of the reason why I gave you the macros, because this is probably brutal to actually try to read. The percent sign in the AT&T syntax is also the format in the printf format string, so you have to put two of them in order to escape it. But this move from offset, this will give you this instruction here. All you do is you give it the offset, which is 8, and you give it the register, which is the destination, and it'll generate this for you. And so move to offset is just the reverse of that. So this is when you want to store a variable in memory. So for like assignment, once you get the value, you use move to offset in order to store it at in the stack frame for that local variable. But hopefully so these arguments are supposed to reflect the AT&T syntax, but also not, force you to have to deal with generating these strings. Questions on this so far? Yeah.
How about this bit off the loading the local variable? You said that you just ask, like, read the ASD and go through what our local variables are and just close it instead of one.
Oh yeah. So let me go to an example. So here's main. So main, just to show you an example, I've written main so that it takes argc and argv, and this is the instruction you call. So first of all, there's code to set up a symbol table, just like in the type checker. So this is the parent of it. So the code supports having like nested scopes, like with compound statements, but it's not required for this course. But I've given you the machinery that'll allow you to do like nested scopes and have different type bit widths. But for the minimum project that I'm requiring, you just need to create the offsets. You need to create the scope to store the symbol table, and then call insert offset in order to add to the current scope, add the name of the symbol, and then whatever its offset is. So for all data in this project, as a simplification, it'll all be 8 bytes, 64 bits. And so when you go to generate code for the function, you'll, just like with the type checker, you'll loop over all of the arguments. And for each one of those arguments, you'll call insert offset for that symbol name. So this will be the scope that you created for that function. This will be the whatever the string in the parameter is, like A or Y. And it'll always be 8 for this version of the project, for the simplified version of the project. But you can use main as a kind of guidepost for what the call looks like. Questions on that? So this is the code that was given to you. So in the simplified version of the project, you only have to deal with one parameter. And I think I've also specified it so that every function always takes one parameter, so you reduce the complexity of this. This is code that will move a register into memory. So this is the move to offset. So because of Intel's kind of more complicated calling convention, the first parameter is always here in RDI. So to make things simpler for ADRA accessing identifiers, inside the function, I always just move all the parameters into memory, into the stack frame. I make space for them into the stack and always move them into the stack frame. So if you didn't do this, you'd have to do more sophisticated register allocation. You'd have to know, oh, my first parameter is in RDI. So depending on whether your variable's in memory or in a register, you'd have to like pick between the two. To make things super, super simple, or simpler, I should say, my convention is to just take whatever the input parameters are and immediately move them into memory, into the space on the stack that I've allocated for them. And this is also why I add the parameters in this part of the stack, because everything is now a negative offset from RBP. But anyway, if you follow main here and just always add a single parameter for the function, so the simplification is that all functions take a single parameter. It should be in the description of the project, but all functions always take a single parameter and only a single parameter. So that way you don't have to do complicated looping or checking whether things are in registers or in memory. So basically you'll always just call one insert offset for the one parameter that the function has. And after the prologue, always look up that offset and move the RDI into that register. So why is it RDI? Why RDI? Seems arbitrary, right? What is yeah. Yeah, it's the calling convention. It's just the calling convention that Intel has. Now, strictly speaking, if you're not interoperating with other like libraries, you could pass parameters however you like. You could do whatever you like to pass parameters. But this is what I suggest doing. Yeah.
Is that line moving from memory to the register?
Yes. Yeah. No. Sorry. This is from register to memory. This is from register to memory. So like, yeah. Always keep in your head AT&T syntax. The destination is on the right. So this is moving. This is the left operand or the first operand to move. And the right operand is being generated by my macro, and so it'll generate whatever the offset is from the base pointer. So let me show this in the assembly code. So this line here, move to offset, is moving from RDI into a memory location. This is the corresponding assembly instruction that actually gets generated from that macro. So RDI is on the left, and then the offset of arg C happened to be 16 here. Happened to be 16. And base pointer, RBP. So yeah, that's what gets generated for move to offset. Does that answer? Yeah.
How's the get RDI to the register?
Oh, so because this is the calling convention that the first parameter always goes into RDI, the C runtime, basically the system, will call main for you. So I only went over this a little bit, but if you notice when you write a C function, main is just a function call. It's not like it just has a different name, like what distinguishes it from any other function. The only reason it's a special function is because basically the system calls main when it loads the function. So you run your program, this is more of an OS thing, but you run the program, and then there's something called the C runtime, which first gets called by the operating system. And that C runtime calls your main. And so there's actually another library that is setting up argc and argv, setting up the memory for that. And then it's actually literally doing a function called the main. And so that function call follows the same Intel ABI. That's how you're able to compile a function that has main in it, and then your system will be able to run it because you're using the same convention. So it's really, you can think of it as the operating system as setting up RDI for you. And then, and we could actually see that. Well, you could actually run a debugger and you could actually see the program running and see that happening. But yeah, you're basically just writing a function that the operating system calls, and it calls using the same calling convention that we're implementing here. But yeah, that's a good question actually. More for an operating system course, but how your function actually gets executed. Okay, other questions? Other questions on this? Yeah.
For other functions, will we have to, will our variables also already be in?
So for your own functions, you'll be putting them in RDI to pass them.
So that's when we go through ASD.
Yeah. So this is this is the actual implementation, but for the more complicated version. So you'll be. Oh, actually, let me show the actual project here. So here's the sequence of steps for making a function call, which I think is what you're asking about. So as I say here, every function that I'll give you for testing will only have a single parameter, and it'll always have a single parameter. So the way a function call works, and actually we have a function call here. So the way this function call works is we'll first compute the value of the parameter. So if it's like 10 times 7 or a plus b, we'll compute that value, and then we'll store that value in RDI per our calling convention. And then once you've emitted instructions to store that value, then you'll use the call instruction, which is an instruction in the Intel architecture. And that will go off, and that will set up. You have code there. It'll actually save the return address, branch to F, and then because of your prologue and epilogue, it'll properly set up the stack frame and set the return value. And once that's done, the return value according to this calling convention will be in RAX. And so after the return, you'll generate code to save that RAX, the value of that RAX. So function calls are an expression. So according to the convention I'm giving you, where should we store the result of that expression in the convention I'm giving you? Just like for the ident expression, yeah. Push it on the stack. So it'll already be in RAX, and just like any other expression, if you just follow that convention of always pushing the value onto the stack, it'll make it easier, in my opinion, to deal with these nested functions. So those are the steps of calling a function in this simplified version. Does that make sense? So yeah, you as the compiler writer are both the client of the calling convention and also the producer of the calling convention. So whenever you generate function calls, you're supposed to be generating them according to the calling convention. And whenever you make a function itself, you use the prologue and epilogue to set up the stack and follow the calling convention yourself. Good questions. Other questions? Other questions on this? So, I know it's a little tedious to deal with this, especially with this convention, which is kind of complicated. But I think going through this process will help you better understand what the machine is actually doing when you're writing programs. And it'll also give you a really good sense of pointers, how pointers work at the machine level, and why C is the way it is, and why you have all these pitfalls in pointers, and what's actually going on in the machine, behind the machine. It'll also help you understand how the suite of system software and the operating system work. They're driven a lot by conventions and just following those conventions. That's why libraries can work together. That's why the operating system can run code produced by the compiler. These are all different programs that have to work together in concert to be able to do all the fun stuff you want to do on your machine. Okay, good questions. Other questions on this? So I think this set of instructions should be, it's basically following effectively one statement. Like if you look in my implementation here, I have these comments around each couple of statements, and this specification basically follows that. So each of these, just like we kind of showed in that top-down approach, that program refinement approach for the type checker last time, can kind of use a similar approach here, where each one of these gives information about what code should be used in order to generate your assembly instructions. And then it's just a matter of knowing the AST well enough, or having the AST.h open, knowing the tools I've given you, like insert offset, and there are examples of this in main, using the convention that I described here, like pushing onto the stack, always using REX as the destination. And hopefully, together, gradually, you can get this, get your compiler to actually produce code that will actually run and be equivalent to your input program. So I've listed out these conventions here. We're going to use the stack to hold intermediate values. I've given a little example. Other questions on this? Yeah.
Are the bonus functions only available for project 3, or do you have functions in project 4?
Yeah, you can work on it. You can work on it at any time. They can be submitted separately. You can basically just come to my office and show me what you worked on. For the bonus points. They don't even have to be submitted with the project. I did also receive a question about whether you can do project 3 and 4 at the same time. And you can. It's just this semester I separated the GitHub repositories for project 3 and 4, just to make it a little easier for you to work on the project. In the past, it was one repository, but it's complicated because if you want to use a pre-compiled version, you have to get the object file. So I just set that up into separate repositories. But you can just literally copy your code generator into project 4 if you've already implemented it for both. You can certainly do that. All right, questions? Other questions? So hopefully, I think you should have most of the tools to get project 3 done. Yeah, okay. Let me go to... So here's an example of what we talked about today using ident expression. So this shows how you can call the lookup into the table to get the identifier, and here's that move from offset. So recall that the way at least I suggested we compile a variable usage is to just take whatever value it has in memory at that stack offset, the offset from the base pointer, and put it into RAX, and then push RAX. And so this is that exact the example of actually generating, for instance, this code. Move from the offset to RAX and then push RAX. And so now hopefully you'll understand why it has this seemingly unnecessary amount of steps to do this. But the goal is just to make it simpler to write each individual code generator function so that there is no complicated communication between them. That's why we have this convention. So, one kind of side goal I have for you with this project is to basically think compositionally. Think about how you can break a problem down into simpler pieces that you can focus on individually, but design their interfaces so that they work together in concert correctly. And making that interface as simple as possible and those contracts really simple makes it easier to have correct code, even if it may not be as performant. But you can always do performance optimizations later after you have your architecture. Trying to think if there's really a case where you really need to do a lot of re-architecting in order to have high performance. And the compiler, for this case, not really, because you can have separate phases to improve performance. There may be cases where, you need to re-architect for performance. But focus on correctness first. Just like with the type checker, go slowly. Go take the parts lower down in the tree and write lots of test cases yourself and make sure the code generation looks the way it's supposed to look. Use GDB, like I showed, I think last time, and I think there's a little tutorial in here on using GDB. Use GDB to actually step through the program to make sure the variable, the registers and memory have the values that you expect them to have. And so this is project 3. Other questions? Questions on project 3? All right, let's take a break here. I know there's a lot of information, but let's take a break for 10 minutes. Let's come back at 11:10 and move on to pointers. All right. So just to point out that, like in C, you can do pointer arithmetic, where you can actually add and subtract numbers from pointers, and so now this shouldn't be that surprising because they're just data. So they're just bits in a register. So if you use an add instruction on it, it will just do an add, even though it might be used later in a memory lookup. Okay, so as a final example, let's take a look at this program here to kind of tie all this together. So we've got 2 variables being declared, and so where are their memory locations? These 2 variables, where do they get stored? Stack frame, good. And the compiler has known offsets from them, -8 and -16. And we have another variable z here declared as a pointer. Where is its memory located, or where does the compiler associate its memory?
On the stack, offset -24.
Also on the stack, offset -24, so -8, -16, -24. Okay, we assign x to 1, we assign y to 2, and then we assign z to be whatever the address of x is, -8. So it's a very tricky one here. And then we dereference z. So just like before, we have an address of x, and then we dereference. That would normally be 1 if we dereference it. But here we subtract 8. So what happens here when we dereference z after we subtracted 8 from the address of x?
It's going to dereference y.
It's going to dereference y. Okay, so we had the reference to the address of x, and then we subtract 8, and somehow magically we now have the value of y. Why is that?
Because you have the address of x, right? And so that's going to be like some value like F7, and then when you subtract 8 from that, it's going to go to the next memory address in the stack, which would be y, since that was immediately after that.
Good. Yeah, so to show this visually, we have stack allocations for X, Y, and Z. We assign X to 1, Y to 2, and then Z gets the memory address of X. So to put some real memory addresses here, let's say we start at FF. This is F7, EF, and E7. So we take the memory address of X, which is F7, and then we subtract 8 from it. So if we subtract 8 from F7, what do we get? EF, unless my math is really bad. So we get EF, and that's the value that's stored in Z. And so just like when we dereferenced Y, it's stored, or when we dereferenced X by itself and then checked the value, we got F7. But here we actually did some pointer arithmetic to change the memory address that Z is pointing to. And so when we dereference Z, what memory location are we actually hitting? Well, it's EF. And EF happens to also correspond to what the compiler thinks is the memory associated with Y. And so that's why that program will actually print out 2. It'll print out the value of Y because we've gotten the memory address of X, and then we move 1 offset down because 8 is the same offset we use to store local variables. And because Y was stored right after X, and we subtract 8 from the memory location, we move down to the next element in the stack frame, which is the entry associated with Y. Yeah?
How does the typecasting work?
So in simple C, I made it so none of these arithmetic operations could work on different data types. So that's why I'm using the typecasting here to force 8 to be a pointer in the pointer type. In C, that's not necessary. They allow you in limited ways to do arithmetic with integers, and they have some silent kind of casting going on. But to make our type checker simpler, I just didn't allow, I made arithmetic operations only work on the same data type, and so that's why I have this cast here. Yeah.
Okay, so it's just, okay, so it's still doing -8.
It's still doing -8. It's just getting around the type system. If we had type rules that don't allow integers and pointers to be computed on together, so this just gets, by the cast will just trust the programmer to change the type whenever you want. That's really all it can. I mean, well, in C, the cast will do memory conversions as well. In our language, it just says, okay, I trust you that that's the new type. Yeah. Was there a question?
I'm just saying, so like, I guess we don't do in C the way if you have to point in the cast, I guess, but in C it would be like %x minus 1, it would check the underlying type of the pointer to X, and then it would say this thing about multiply after you're subtracting by the amount of bytes.
Yeah, that's right. Yeah, it would, yeah, that's true. So the pointer arithmetic in C is more sophisticated. It uses the size of the type. And so 1 is like 1, whatever size of the type is. You're right. Yeah. So that doesn't happen here in this language. It's much more literal. So it's just literally passing the values to the add instruction. So to simplify this, I made everything like the same type. There's no type coercion. There's no fancy casts. There's no fancy arithmetic. But you're absolutely right. It would, it would be much smarter about that. Kind of like arrays. So with arrays, the offset is multiplied by the width of the type. So that's why you have, when you say 1, if you have an array of integers and you say, give me offset 3, that's not 3 bytes. That's 3 times whatever the size of int is. But here, this is much more literal byte level manipulation. So I'm not going to give you programs to do this. You don't have to actually program in this. But I just wanted to illustrate that this kind of brings together all of the different pointer operations that you have in C as well, and it shows the stack layout. What happens with the stack layout? And this is actually the source of an enormous amount of security headaches. This kind of messing with the stack layout. If you ever heard of stack smashing attacks or buffer overflow attacks, this simple little example illustrates why those happen. Because the compiler has some convention about where data is stored in memory, and if you can just write wherever you want in memory, then you can blow away that data, and that could have really bad security consequences if that's, say, a password or a Boolean that says, hey, you're authenticated. You can mess with that by overwriting values on the stack. All right, questions? Questions on this? So that seems like a good point to stop. Next time we'll finish up this project. I'll give you the project overview, and yeah, good luck on project 3.